Is one of the simplest topics of the entire year. It's called the intermediate value theorem. It's going to sound so silly you won't even believe there's a name for this rule. If f is continuous on a function from a to b, notice the interval there is a closed interval. So f has to be continuous on the closed interval from a to b, so including a and b. So let's draw that. We're going to need an a and a b as x values, and we're going to need a function that passes through a and b. This is f of x. K is some number between f of a and f of b. So we have these two values on the y-axis, f of a and f of b. And we'll get more used to this as we get into the next section of the class. But you've got to be good at translating this when you read it in a sentence as two different y values. So they go on the y-axis. And k is some number in between. Any number in between f of a and f of b. The intermediate value theorem states that there must be at least one x value, c. So there must be one point here, not sure exactly where it is, but somewhere in between a and b, there is an x value, such that f of c equals k. That's it. The point is, if a function goes from here to here, it's got to pass through every point in between, at least once. It can pass through those points more than once. It's just got to be at least once. That's the intermediate value theorem. It seems pretty obvious when you say it that way. You can't get from here to here without passing through the points in the middle. That's it. You can use this a little bit. So some examples of how you use this. For f of x is x squared minus 5x plus 2. Prove that there exists a value, some x value, x equals c, such that f of c equals 4. In order to do that, all you need to do is set up that first part of the theorem. We call that the hypothesis of the theorem. We need to find an a and a b such that f of a and f of b has the k that we're looking for. In our case, that would be 4. That's the y value in between f of a and f of b. We just need to pick a value for a and b such that f of a is below 4 and f of b is above 4. Well, we can pick whatever we want. F of 0 is equal to 2. I can find the y-intercept of that really quickly. And f of, 10 is equal to 100 minus 50 plus 2. So we can say that because we have a function that goes through the point 0, 2, and 10, 52, I don't really care that my drawing's not to scale here, there must be some x value where the function passes through 4. That's it. That's all I need. At some point between the point 0, 52 and 0, 2 and 10, 52, the graph has to pass through C4. That's it. All I know is that it exists. And then the question did ask to find that value, so we want to know when does x squared minus 5x plus 2 equal 4? And this one we'll have to use the quadratic formula because it doesn't factor when I subtract 4 from both sides. So that won't factor. So x is equal to 5 plus or minus the square root of 25 minus 4ac, so that's plus 8 over 2a. So 5 plus root 33 over 2, and 5 minus root 33 over 2. Those are the two values. Okay, this last question here is the last thing we'll do. An example of a function that is continuous on, notice, the open interval from a to b, and the IVT does not hold. So, for example, if you had a function with an a and b on the x-axis, if you had a function that was continuous on the open interval from a to b, sorry, I didn't draw this very well here. Continuous on the open interval from a to b. Notice how that does not meet our hypothesis for the theorem, because f of a is up here, f of b is down here. Still didn't draw that very well. Let me move this down a little bit. I could pick a y value that is in between f of a and f of b, but there is no point where my function passes over that y value. So because my function was only continuous on the open interval from a to b, not the closed interval from a to b, the IVT doesn't apply, and you can see this is an example where the IVT doesn't actually prove to be true at all.